like to consider an example of the use of Cauchy's law. So let's consider a body, and let's go ahead and determine the force per unit area at two different points in the body, at the point A and at the point B. So we have A here and we have B here, and let's go ahead and determine the forces per unit area acting across some cutting planes passing through these points. So at B we'll have a section cut in the 1, 0 direction, so in the x direction, and at point A we'll have a cutting plane or section cut at 45 degrees. And we'll assume that the body is in a homogeneous state of stress given as follows. So the normal stress in the x direction is 10, normal stress in the y direction is 5, and the shears are 1 and 1, and we know that the shears on orthogonal planes have to be equal to each other, and the units will be KSI, so thousands of pounds per square inch. So this is an ideal problem for the use of Cauchy's law. And so, for instance, let's also find the normal and shear stresses on the surface. So Cauchy's law tells us that sigma transpose n is equal to the traction vector, so that's the force per unit area on the section cut with normal n, and that's exactly what our question involves. So at B, for instance, we can multiply the stress by, or the stress transpose, and since it's symmetric, it's actually the same thing, times the normal vector gives us the traction vector, which in this case is 10 ksi in the x direction and 1 ksi in the y direction. So to get the normal stress on the section cut, I now take the traction and dot it with its normal vector itself again, which is 1, 0. And so I get 10 ksi, so that's the normal stress passing, or on that plane, passing through that point. And then the shear stress, I have to take the dot product of the traction vector with a tangent vector to that surface. So let's say S. And so S is 0, 1, and I take the dot product with 10, 1, and I find 1 ksi. So there's a shear of 1 ksi on that plane and a normal stress of 10 ksi. If we now consider point A, we can compute the traction on the surface with normal 1 over root 2, 1 over normal root 2 by simply taking sigma transpose and multiplying it by that normal vector. And if we do that, we end up with the traction vector that is 11 over root 2 in the x direction and 6 over root 2 in the y direction, ksi. If we now want to know the normal stress on that surface, then we simply take the traction vector and we dot it with the normal vector. And if we go through the calculation there, we find that we have 8.5 ksi on that surface. So that's a tensile normal stress there. If we want to find the shear stress on this surface, here we'll take the traction vector and we'll take its dot product with the tangent vector, which in this case is minus 1 over root 2, 1 over root 2. And if we go ahead and we compute that dot product, we find out that we have minus 2.5 ksi. So there's a shear stress on the surface, and it's pointing in the opposite direction of the vector S.